This is R.4, a continuation. We didn't get to finish what we started in class today. So what I'll do is I'll go ahead and finish that on my own. This is a video I'll be posting on YouTube, and I'll be posting it on each of the class periods that I have for Precalculus pre-AP. Pretty much everybody got started with example 3, but we didn't get to finish all of example 3, and I'll go ahead and do that. So the class where I got the furthest in, we did A and B. That was 4th period and 8th period, I think. So we got to start in first period, so we caught up quite a bit in first period, which was good. But we didn't get as far as I was hoping we were going to, so I'm going to eventually have to slow stuff down. So I attempted to do like one section today. So one section yesterday, R.3, that failed. One section today, R.4, and that also failed. But I don't know if it's because I went too slow for R.3, that I was still trying to catch up. That division problem took a long time. So we'll continue. I'm going to continue trying to pace this properly, which is still new to me when it comes to planning this stuff because of the asynchronous versus synchronous stuff. It's really tough to try to plan for that. It's easier when you have 5 days out of the week to teach new stuff. So we'll continue. What we're doing is we're factoring each of these if possible. It should say if possible. Yeah, it does. So example 3, factor each trinomial if it's possible. So we'll continue with letter C. 2x squared plus 13x minus 18. So what we saw in class is we apply grouping if it's possible, and if it's possible, we're able to factor such a thing out into 2 linear factors. So like we saw for letter A, this polynomial, which is a trinomial, factored out to 2 different linear factors, 4y minus 3 and then y minus 2. Same thing with part B, and part B was a little quicker once we know what the scheme is. So for part C, so we'd have to know what the scheme is. What you do is you take the leading coefficient, which is 2, multiply it with the constant, which is negative 18. 2 times negative 18 is negative 36. And this is probably something you want to do ahead of time before you start factoring. Actually, there's another thing that I'm skipping. The very first thing I advised you guys in class, check for a GCF. And in my mind, I already saw it, and I saw that there was no GCF, so I kind of skipped it, but I need to address it. 2x squared, 13x, 13 is a prime number. So that's probably going to kill it right off the bat. And then negative 18. So since negative 18 is a constant term with no x value or no x variable in it, and 13 is the numerical portion that's actually prime, we don't have a GCF between those 3 terms. Whenever we do have a GCF, though, you want to factor that out first before you start any other methods. That is the first thing you want to try. So I skipped that and I went over to the trinomial method where you try the expansion, so that way we can try grouping. So you multiply the coefficient, the leading coefficient, with the constant negative 18, we get negative 36. So then, the requirement now is, or the thing to do now is to split up the middle term into 2 other x terms that sum up to positive 13. So I need 2 numbers whose sum is positive 13. However, the other condition is they must multiply to negative 36. So they must multiply to negative 36, but they have to add up to 13. So it might be kind of hard to see right off the bat. Now one of them has to be negative to make a negative 36. So if it's not something you could see right away, you go down the list. 1 and 36. But that's not going to make 13 in any way, shape, or form, so you keep on going. Then you bump up 1 to 2. And that's divisible by 2, so we'll leave the 2. 2 times, what is that, 18? And 2 and 18, there's no combination that would give us a 13. You bump up that 2 to a 3, if 3 is one of the factors, and I think 3 divides 36. 3 and, I think it's 12. 3 and 12, they don't have a combination where I could make 13. I think it's divisible by 4 as well. 4 and 9 would be the case. I think it's 4 times 9. So that situation, if I were to add those straight, I would get positive 13. The problem is because we have a product of negative 36. One of them has to be negative. So in the event where one of them has to be negative, I'm either getting 5 or a negative 5, and that's unfortunate. So that one doesn't work either. So then 4 times 9. The only other thing I know, since that's not divisible by 5, that's the next number up. The next one is 6 and 6, and we have to subtract them. So one of them is negative. So that would give me a 0. And I think I've exhausted all possibilities. And I've not found a pair of numbers that will multiply to give me 36 and also add up to a positive 13. So since there are no, these are all possibilities, all combinations, and none of them go anywhere, we say it's not factorable. If you wanted to sound a little smarter, we say that the polynomial is prime. Just like with numbers, there are such a thing as prime numbers, numbers that cannot be broken apart into smaller primes, other than 1. Right? So 1 is technically not a prime number. The first prime number is 2. So polynomials can also be prime if they're not factorable, just like numbers. So we call this prime. It is not factorable. So sometimes that's a possibility. And on the homework, I didn't actually check all of them. There might be 1 or 2 of them that are actually prime. So you'll have to know when that actually happens. We'll look at letter D. And for letter D, 16y cubed plus 24y squared minus 16y. And here's probably where that advice I gave you guys earlier is going to be helpful. If you look at all 3 terms, very first thing you want to check is for a GCF. And it looks like there's going to be a GCF other than 1. Unlike this situation where there was no GCF, so not factorable whatsoever. So this one at least has a GCF, it looks like. 16, 24, and 16, they're all even numbers, so at the very least, I can move out of 2. I want to find the biggest, though. 16 and 24 are also divisible by 8, I think. And I think 8 is the largest numerical value that divides all of those. So let's try that. I'm going to call this equal to 8. And if I look at the y terms, every one of those terms has a y to spare, but at most 1. So the minimum is 1. 8y goes outside. I'm left with 2y squared plus 3y minus 2. And if I did this right, then the inside should not have any common factors. So we should not have anything else that we can factor out. 2y squared, 3y, negative 2 has nothing in common. Or there's nothing collectively in common. So then, that's a trinomial on the inside that I'm trying to break apart. So 2y squared plus 3y minus 2. I'm going to do that on the side. And I'd like to break this apart as 2y squared plus something, and then a minus 2, where I'm going to split up that middle term if possible. So this just happened where we found one that wasn't factorable. It's possible it's going to happen again. Hopefully not. So then in this case, what you do is you take the leading coefficient and the constant, you multiply them. In this case, that's 2 times negative 2, which is negative 4. So negative 4, I need 2 numbers whose product is negative 4, and their sum is the coefficient on the middle term, which in this case is positive 3. So negative 4, positive 3. That'd be negative 1, positive 4, I believe. Negative 1 times positive 4 is negative 4. And then 4 minus 1 would give me positive 3. So it looks like this one does work. And that one was very simple, unlike the other one before. So then minus y plus 4y is what we expand that into. So we check negative y plus 4y is the 3y that we got originally. So that's equal to this. And then we carry out the grouping procedure. Look at the first one. The most we can group out there is a y, it looks like, and I'm left with 2y minus 1. So you're going to want to go back to the extra factoring by grouping video that I gave also on the Google Classroom page. So there should be one there under just factoring by grouping. And I think I'm going to go ahead and lump together GCF with that one. Okay, so 4y minus 2, this can be plus 2 that I'm going to go ahead and factor out. And we're left with 2y minus 1 if you factor out a 2. And then we notice that the 2y minus 1 is a common factor for both. That's going to get moved out as a GCF, basically. 2y minus 1, y plus 2. And this one's completely factored. I would want to box that, but that's not the final answer. That's just what this one becomes. So the final answer would be that which I just got, multiplied with the 8y that was factored out from the beginning. So don't forget about the 8y GCF that was factored out at the beginning. 2y minus 1, y plus 2. Let me double check that's all correct. And yeah, it looks fine. So then this is what I'm going to box. And there's the work on the side to factor the stuff inside parentheses. So that's the basics behind factoring those types of trinomials. This is a slightly more complicated one where we also had to apply the GCF procedure before. Now, if you did not use the GCF procedure that you did before and you went straight to the leading term times the constant method, the AC method, it might not have worked out for you. So we're going to move on to factoring special polynomials, and we're going to talk about specifically perfect square trinomials, which I skipped in the previous section because we were going to see it again here anyway. So I didn't want to cover that stuff twice. So perfect square trinomials, you can go forwards or backwards. If you want to factor, you're going backwards. If you're multiplying them straight, you're going forwards. Let's talk about the forwards problem. So perfect square trinomials. You can get a perfect square trinomial by taking a binomial and squaring it. So let's say A plus B, and I'm going to square that. Now the way that you would normally square this, I'm going to do this visually so it's a little easier to see. I'll use the box. Let's see if I can zoom in on that. A plus B, A plus B. Since it's A plus B squared is the same thing as A plus B times itself. That's the proper way to square something. You multiply it with itself. So that's why I'm multiplying A plus B, graphically speaking. So then you multiply these each. A times A for the first one is A squared. A times B for the second one, that's AB. You just write them together in juxtaposition. Same thing for the next one, B times A. But we said earlier, commutativity property for multiplication, A times B is the same thing as B times A. It doesn't matter the order you write them. So that's again A times B, even though it doesn't look like the same order. And then B times B is B squared. So then, if we did this properly and there were no missing terms, diagonals should match. They're like terms. So I have two ABs. And if I write this all the way out, this ends up being A squared plus 2AB plus B squared. And that's the perfect square trinomial formula. So that's one of them. We can vary this a little bit by varying the sign inside. If I subtract A minus B and I square that instead. You can try this on your own, use the box again. Final answer is going to be A squared minus 2AB plus B squared. It only differs by that middle term. And the sign is the only thing that differs. So those are my two perfect square formulas. So we'll also add on some practice problems where we reduce these perfect square trinomials, or maybe try to identify perfect square trinomials if we don't know that they are. And once we do know that they are, we can use that shortcut. So it says factor each polynomial. And because this one's a trinomial in this case, and I notice the first and the last are squares, it might be a perfect square, just like this thing here, or this thing here. And since the middle term is negative, I'm not considering this option. I'm considering that one only, the negative one. So do these match up? Question mark. Are those the same thing? So is A perfect square? Is it of the form of this one? Maybe, maybe not. We're going to check. Here's how we check. I'm going to compare this with A squared minus 2AB plus B squared in the original formula. If that's a perfect square trinomial, then 16p squared is equal to A squared. So what I'm doing is I'm doing like a very dry, cut and dry sort of like comparison, but I can try to simplify this as much as I can, as much as possible. The idea is A squared is the square of something. So what we're going to do to find out what that something is, we take the square root of what's there. So square root of 16p squared. What did we square in the first place to get 16p squared? This is telling me that A might be 4p. Because 4p squared, 4 squared times p squared is 16p squared. We do the same thing with the last term, positive 25q squared. This tells me that b should equal to 5q. If I squared 5q, 5q times 5q is 25q squared. So far, that's what A and B should be if this is a perfect candidate for perfect square trinomial. there's a third condition, the middle term. When I plug a and b into the formula, negative 2ab, I'm supposed to get negative 40pq. Let's try it. Negative 2, and we're requiring that a is 4p and b is 5q. So then let's simplify. So is this equal to, question mark, 40, negative 40 pq? And you could check it. Negative 2 times 4 times 5. 4 times 5 is 20, times negative 2 is negative 40. And then there's a p, and then there's a q. And that one does work. This one is a perfect square. So what I did here was I just checked to see if it was a perfect square. I verified that it is a perfect square. But if I stop there, I've not answered the question. I've not finished all the way through. So what's missing? What they're actually asking me to do is to factor that polynomial completely. So I need to find out what the factorization scheme for that thing is. So here's the factorization scheme. Since I've verified that it does fit the pattern on the right-hand side, a squared minus 2ab plus b squared, then I'm good to go backwards to this factorization scheme, a minus b squared. So what you do is you follow directions. This is what a is, this is what b is, and you plug that into the formula, a minus b squared. So then that's 4p minus 5q squared. And then I'll box that because that's the factorization that they were looking for. And that's completely done. And of course, I'll have some more videos on how to do more of these. There's a part B, which I'll definitely do. So again, if it's factorable, it should follow that exact same pattern. A minus b quantity squared. A squared minus 2ab plus b squared. So this is a squared. This one's b squared. And this one's supposed to be 2ab. Positive in this case. So the sign in the middle, if that's positive, that just means that in the factorized version at the very, very end, it's going to be a plus. That's the only difference. So these are technically the same if you remember the difference. Middle term is positive, then the middle term is positive. If the sign in the middle is negative, then the middle term is negative. Easy to remember, in my opinion. Hopefully same for you guys. So then for this one, what you're going to try to do, the procedure here, is to boil down those outside terms and rewrite them as squares. So boil these down as squares of something. 36x squared y squared, hopefully you're okay with this. This is 6xy squared. 49 is 7 squared. That's an easier one, way easier one. So if that's the case, a is 6xy, b is 7. So you take away the squares in your mind to find out what a and b are. So then I have to check, is 2ab equal to 84xy? Question mark. So I'd have to double check. So then we're going to plug it in. 2a, which is 6xy, times b, which is 7, is that in fact equal to 84xy? So then you multiply. 2 times 6, 2 times 6 is 12. 12 times 7. What's 12 times 7? That's 80, is that 84? Let's see, 6 times 7 is 72, so another 12 is 84. So yeah, that's right. I had to pause there for a little bit. I had to think about that. But yeah, it's 84. And then 8 times 12 is 96. So yeah, they do multiply out to that. So that's 84xy. That's a check mark. So if that's the case, if that checks out, this is a not a difference of squares, a perfect square, and that thing factors out to a plus b quantity squared. 6xy plus 7 quantity squared. So those are special trinomials. We'll look at special binomials, difference of squares, difference of two cubes, and difference of two, or sum of two cubes. And that's going to conclude this particular section. I thought there was going to be more after that, but apparently not. Okay. So difference of two squares. This is another shortcut you want to memorize eventually. Practice a lot in the homeworks. So the difference of two squares. A difference of two squares is a number that's squared minus another number that's squared. Or if they're polynomials, they're much more complicated situations. And this comes about the multiplication, or this comes from the multiplication of a minus b with a plus b. So a minus b times a plus b. And you can verify with the box. A, b, a, negative b. A squared, ab, negative ab, b squared. ab, negative ab will cancel each other out. They're like terms. Oh, not just b squared. b times negative b would give me negative b squared. So you have a squared minus b squared, just like in the formula. That's the only thing that survives. The difference between two cubes, a cubed minus b cubed. This factors as a minus b, a squared plus ab plus b squared. And you can verify by multiplying these two in a 2 by 3 square or box. It's not a square if it's a 2 by 3. 2 by 3 box or rectangle. And you'll get a cubed minus b cubed, which I will not verify here. If you want to try on your own, you can verify on your own. It's a very good little instructional step. It's good practice for the stuff we saw in the previous section, multiplication. The sum of two cubes, and this is a cubed plus b cubed. This one factors out as a plus b, a squared minus ab plus b squared. And again, you can verify that using a box, which I won't. So those are factorization schemes. And the names tell you what to look out for. You have the difference of two squares. Difference means you're subtracting. So you're subtracting two square things. The difference of two cubes, you're subtracting two cubes. And the sum of two cubes. Summing is addition, so it's the addition of two cubes. So those names are a little bit better. Perfect square. Perfect is kind of a weird word, or a word that doesn't really have like a mathematical meaning other than the one that we assign here. We call it a perfect square, I guess because it's some sort of aesthetic thing. Here it's more straightforward. The difference of two squares, and it is what it looks like, or it looks like what is being described. And we should be able to see these and try to identify what those are. So it looks like the first one, that's not so obvious because we have fourth powers here. But fourth powers are even powers, and even powers are multiples of squares, because squares are 2, and 2 divides every even number. So we can think of that as a square. And because that's a square then, and this one's a square, and we're subtracting, this seems like a difference of squares. So then that's a squared minus b squared, which the formula is a minus b, a plus b. That's the formula. So then I have to think of these in terms of squares of something. So 256 k to the fourth is the square of some other number. 256 squared. What is 256 squared? I don't remember. Is that 16 times 16? Let me just double check. That's kind of embarrassing. I gotta check. Yeah, 256. So 16 squared. So that's going to be the square of 16k squared. Because when you square a square, you get a 4. You multiply 2 and 2, you get 4. Minus 625. What is that the square of? I believe that's the square of 25. And yeah, that's 25 squared. So 25m squared, because that's another fourth power. And then we square that. So when we square a square, we get a fourth power. Now that we've successfully found out what the value of a and b are, then we simply plug into the formula a minus b, a plus b. So then this is equal to, factored, 16k squared minus 25m squared times 16k squared plus 25m squared, a plus b, a minus b. And I would say we're done here, but we're not. So if you inspect both of these, so when I went over the procedure, the checklist for factoring things 100% completely, First thing you checked was GCF. The second thing you checked was how many terms there were. Oh no, that wasn't the second thing you checked. The second thing you check is if it's in standard form. Standard form is just if it's in order, and this one doesn't really have an order. They're both equal degrees. So that one's one that we skipped. Then we count how many terms there are. In this case, there's only 2. So one of those things that we're going to be looking out for when we see 2 terms, it's called a binomial. Is it a special binomial? And in this case, it was. We figured out that it was. It's a difference of 2 squares. So then we apply that formula. At the very, very end, if you've factored some stuff out, you check for the degrees of what's inside of those individual factors. Both of those degrees are 2. Anytime you have a degree bigger than 1, it might still be possible to factor further, so you check them individually. So then again, you go through the checklist, but within that group. So for the first group, I count 2 terms. It's a binomial again. Is it a special binomial then is what goes off in my mind. So if there's 2 terms, it might be a special binomial. Still, there are 2 squares being subtracted. So this right here is another difference of squares. This one is not one of the 3 there, and it wasn't listed here. There is no sum of 2 cubes in this list, and there's a reason why. You can't use a scheme with the box to figure out how to get a squared and then plus b squared. Unless, of course, you go outside of the real numbers into imaginary numbers. So there's a way to do it, but you have to do this using imaginary numbers. So at the moment, there is no formula that we're going to go over yet that will produce the difference or the sum of 2 squares. It just won't happen at the moment. We'll go over that in chapter 1. We'll see that again in chapter 1. But not now. So this one is not factorable. The 16k squared plus 25m squared is not factorable. The first one is. It's a difference of squares. A squared minus b squared. And what's 16k squared the square of? It's the square of 4k. 4k times 4k is 16k squared. And then I subtract. What squared gives me 25m squared? That should be 5m. And we vary it. 4k minus 5m, 4k plus 5m. And the other one is not going to be factorable. 16k squared plus 25m squared. And because nothing else there is factorable, that problem's done. So then we'll look at part B as soon as I resize this because it's kind of cutting into the space where part B is at. Looks a little annoying. So the letter B, which I'm going to zoom in on more. So letter B, 8q to the 6th power plus, it's a sum, that for sure, 125p to the 9th. So it's a sum of two monomials, so it's a binomial. And the only thing I see here that's a sum of 2 things would be the sum of 2 cubes. So then I'm minded to think about whether or not those are cubes of something. So that's what I'm going to have to ask. Is that, or are those the cube of something? So I know q to the 6th. 6 is a multiple of 2, or a multiple of 3, sorry. It's 2 times 3. So q to the 6th is the cube of q squared. So let me write that down here. Q squared cubed is q to the 6th. So q to the 6th is definitely a cube. What about p to the 9th? 9 is 3 times 3. So p to the 3rd is p to the 9th. You multiply those powers. So those are definitely cubes. Let's talk about the numbers now. Is 8 a cube of another number? And is 125 a cube of another number? Specifically whole numbers. 8 is the cube of a whole number, the number 2. 2 times 2 times 2 is 8. So then this is 2q squared cubed. The next one, this is plus 125 is the cube of 5. 5 times q to the 3rd power. Or not q, sorry, that's p. Cubed. And then what we do is we follow the cube formula, the sum of 2 cubes. Sum of 2 cubes, a cubed plus b cubed, boils down to a plus b. A squared minus ab plus b squared. Okay, so then I'm going to have to follow that formula. A is the stuff inside of the first cube, b is the stuff inside of the second cube, and then we just follow suit. So then it's going to be a plus b, literally 2q squared plus 5p to the third. That is the a plus b step. The next step, we square a. So a is 2q squared. We have to, and we have to square that. 4q to the fourth plus a times b. Let me zoom in. I accidentally zoomed out. So then minus, in this case, you multiply a and b. So that's going to be minus 10, because 2 times 5 is 10, q squared, p cubed. Those do not combine. And I'm probably going to want to scale this one back a little bit. It keeps zooming out. I don't know why. So I'm just going to move this a little further up. Okay, and then the very, very last term, plus b squared. So I have to square 5p cubed. So that's 25p to the sixth. And then we check. This weird thing, that's a fourth power trinomial. That's not something I'm going to have you guys try on your own. So you can stop there at that step for that one. If we have the difference or the sum of two cubes, the one that's left out, for the most part, will usually be not factorable. Unless for higher powers, but there's no way that I'm going to require that you know what to do with those higher powers. So fourth power is too high for now. The 2q squared plus 5p to the third, there's two terms there. They have nothing in common. That's not a sum of cubes anymore, so that's going to have to stop there as well. So we'll just go ahead and stop here at this step. There's nothing else we can do with that. That's a really ugly problem. Very, very complicated. If you can master something like that, then that's it for this particular section. So there will be homework for this. Make sure you guys check the Google Classroom.